So welcome to Sharing Direct Current, Securing Our Energy from Cyber Threats with Direct Current Microgrids and CurrentOS. We are thrilled to have you join us today. Our hosts are 𝗪𝗵𝘁𝗂𝗆𝗺, who is the CEO of 𝗲𝗵𝗵𝗁𝗺, and Harry Stockman, who is DC expert and influencer. Both are valued partners of CurrentOS. We are also today with Prashant Kurup, who is the General Secretary of CurrentOS, and I am 𝗲𝗵𝗁𝗁𝗁, responsible for marketing activities. Maybe before we dive in for our newcomers, I will start with a few information about CurrentOS, and before that, a few housekeeping notes just before we dive in. Feel free to ask any questions in the chat. We have set aside plenty of time at the end to address your questions and have a discussion. So ask in the chat and we will take your question. Prashant will do the moderation. This webinar is being recorded, so you will receive the recording by email. If you want to share to open your camera and your mics, we are very happy to have you on board. It's more lively when people are with us, looking at us. We know who is here. And of course, follow CurrentOS on LinkedIn, on YouTube. We have a YouTube channel with all our webinars, with several introduction videos about CurrentOS. LinkedIn, it's a way to stay connected with our vibrant DC community. And let me introduce CurrentOS very briefly. So CurrentOS, we are defining an electrical standard for direct current. Today in our world, we have a lot of devices, applications, running on direct current. So direct current is another form of electricity versus alternative current, which is distributed through the main grid. And these devices today are not connected in direct current. So our mission with CurrentOS is to create a standard in order to empower a sustainable world where electricity can be accessible for us all, because we know that the main grid today is going through some strong congestion issues. How is CurrentOS organized? So we are a non-profit partnership. We are a member of the 𝗪𝗵𝘁𝗂𝗆𝗺, for those who know this working group. We are non-profit. It means that it's a group of companies this is list of companies who are members, partners. They pay a fee to join and they access the intellectual property and they can contribute to the intellectual property of these direct current distributions. We are in over 25 countries represented in North America, Europe, Asia. So if you're interested to join, reach out and we'll tell you more about it. And what do we do? What do these companies do? They are developing projects. So they are testing in the field the new standard that is being developed, that is operational already, because we have many commercial projects already on the field. So examples are EV charging stations in parking facilities. We have university campuses, data centers, office buildings, residential houses, street lighting, and many more. So that was for the introduction. Now, without further ado, over to our hosts, Emmanuel and Harry. The floor is yours.
Thank you, Raphael.
Yeah.
I'm very happy to lead this webinar dealing with a strategic topic for everybody, which is cybersecurity and grid. As a consequence of the electrification of use, we are witnessing an exponential growth in electricity consumption of more than 4% per year. This means over 50% within the next decade. Combined with a massive deployment of renewable energies, this makes balancing the power grid increasingly complex, with significant congestion challenges and a major risk of blackout, as we noticed recently in Spain. Whereas for a long time, the grid could easily handle fluctuation in consumption, it's now becoming more and more complicated to guarantee this balance without flexibility tools, which necessarily requires the interconnection of different networks. This raises, of course, the issue of cybersecurity as soon as all equipments and systems are connected and the networks themselves are interconnected. Just for information, a sudden variation of just few gigawatts could then be fatal to the stability of the grid. Harry, you are an expert on this field. What is your opinion on this topic? And what do you think is our level of vulnerability to the risk of a cyber attack?
Yes.
Thank you for your light.
Yes. I think because I think that the risk what we have is massive, really massive, and we really underestimate how vulnerable the system is. And the misassumption is also making the system about the electrical system, because in the past the system was incredibly reliable. So we take really this reliability as a given, and if we start to change our system, then we assume the same reliability. And that's why, to explain a little bit why the legacy systems were so reliable, because everything was planned and very well organized, and everything was analog, and everything was over-dimensional. Everything was in the large how to say, in the high power available. So that means analog, no smartness. And that's why that was also the success why 𝗀𝗃 succeeded in that case, because 𝗀𝗃 was a simple system with simple components that built this massive network in a reliable way. But today we start to change that, and we start to make from our infrastructure what was in the past designed top down. That means we have global generation, and then we distribute, or we transmit and distribute to the users, and the users consume only. And that was very good overseeable with a simple market to balance our system to operate. And it was done with a few players in the electrical system to create the game of balance, because our electrical system should be constant real-time imbalance. You cannot have unbalancing between loads and generation. And that is actually where things becomes a little bit different, because, can you go to the next slide? Yes, because we start to change our infrastructure due to the fact that we move from our energy supply to all electric. Because in the past we're using gas, we're using other fuels, and now we putting more and more to the electrical system, because all electric is a super good idea to do. If you want to save energy, if you want to be energy efficient, all electric is the way to go. And the nice thing about electricity is that you can create it locally. And if you start generating local energy, then things becomes a little bit more complex, because we start to transfer our system from a top-down structure to a new a bidirectional system. And this bidirectional system, of course, then the question arises, how do we manage? How do we manage this complexity when you have everywhere in the system generation, consumption? You have, instead of a dozen of players in a country, you have suddenly a million players in a country who need to be aligned and to be part of the game to make the balance between in the system for the availability. So, and that is creating all these challenges, and that is every time it's a transition. When you want to have transition, you make a plan from A to B. It looks like a straight line, but you go from left to right, you go to all kind of directions, you enter to that line. So you see a lot of new players entering in this market. And one of the biggest players entering in the market is actually a digital player. And this is where things becomes, suddenly we start to change, because in the past it was impossible, for example, from cyber point of view, to attack a relay or to attack a breaker or to attack just an analog measure tool that measure the frequency and try to balance the system with the frequency and with the fuel consumption. That was very simple. But today, with all the inverters, with all the electronics connected, yeah, we start to connect to digitalization. And that makes a huge difference. So if you look to today's grid and legacy grids, yeah, we see a massive transformation of the system. And this is where me as a citizen of this planet makes me a little bit worried, because in this point we have this very reliable old system. We move all our energy consumption live to the electrical system, and that means we cannot live anymore without electricity. And that so if a blackout happens, like in Spain, you clearly see in a blackout of 24 hours what a mess is made, and nothing is working. The water is not working. The wastewater system is not working. Nothing is working. So, and that's why we have this webinar, actually, this discussion. How do we can address that?
Yes.
And that is, and to explain a little bit the issue is because if you compare to the past, you see clearly a top-down structure. And in top-down structure, you see, okay, you transmit energy to the subscribers, to the consumers, actually, and then in a system you call them subscribers. And then you have the market, and the market is only looking to the frequency. If the frequency is going down, okay, price goes up. If the frequency goes up, the price goes down, and that makes it easy for the energy providers. Okay, if the price goes down, okay, then you have to reduce to the gas consumption, because then you will start to overproduce, and that was simple. But during the fact that we start to enter in the local part in the system, we start to enter new sources in the system that are randomly injecting energy without proper coordination. And by the way, the sun and the wind are very dominant energy providers, but don't never look to the price. So the sun never stops shining when the price is too high, or other way around. So you get a very irritant, disturbing players on the energy market. And this makes the system more and more challenging for the market to manage. And particularly when the system is interconnected, yeah, you get massive energy flows from one continent, one area to one areas, and all these kind of things, and that need to be transported to be managed. And one of the ideas is that, can you go to the next slide? Yeah, one of the ideas is that, okay, let's connect things with controllability. So if the market becomes a little bit too hot, maybe we should curtail some PV inverters, or we should enable some EV cars. And maybe we have to slow down the HVAC, or we have to increase the HVAC. These kind of things, that makes a lot of sense if you look to the existing asset we have, because what I say, it is a simple system with simple components. But when we start to change the system, okay, then you come to a very difficult question to answer, because how do you manage that simple system not to be overloaded? And this is what I want to say. This is a very difficult topic, because if you look to system design, one of the rules in system design is that you should not mix other systems. If you start mix other systems, then you come to the point, okay, if something goes wrong, which system is causing the fault and which system is right, which system was wrong? You get this kind of interconnection. So that means we start to build from new market models, from new business cases, new services on this existing simple system with this digital layer. And then we start to maintain that electrical system to keep the lines in relationship. So we start to prevent, for example, that the fuse will be tripped. We start to use this with digitalization. And this is a very, very strange situation, because just as an example, there are few big players of inverters who organize services to manage the inverters, and they can easily turn off and on these inverters from remote places. And that technically means if one of these companies are hacked or they have a bad intention, they can break down the systems. Because and if you have a big player on the market for solar inverters, they can shut down, for example, like in Europe, I know you can shut down 22 gigawatt of PV from a remote location. And this 22 gigawatt is very hard for the system to handle. The same if you are a charge point operator, and like in the Netherlands, we have 100,000 public chargers. If you, if this was one player and this player want to control through the internet, you can easily disconnect these 100,000 chargers, so you can have a huge interruption in the system. And this is what's worrying me. And
sorry, Ari, it is also the same with smart homes systems.
Yes. Yes, smart home
today
systems.
You have companies who are deployed massive IoT in housing, more than 1 million solutions, and here also 1 million solutions at once. It can generate a blackout.
Yes, and just to give a stupid example, I have one lamp in my house. I'm monitoring my data traffic of my smart device in my home. I have one lamp that is communicating 30 megabyte to a data center somewhere in the world. I don't know what it's doing, what is happening there. They can do remote firmware updates. They can do all these kind of things, and this happens in the background. And this is it makes it very, in one way scary, in one way super good, because we create new businesses, we create new business models, we create new markets, we create new solutions, we create innovation, and actually we create new problems. And when you have problems, okay, you have new markets and new possibilities. So that is the good thing about it. But there's one thing I like to
highlight.
To highlight, yes, because if you, for example, to make an example to demonstrate a little bit what we are doing, because our life is depending on the electrical system. But now, if we make our life depending, if we sit in the car, we make a physical dependency. And if we sit in the car and we sit in the brown car in the left side, and you sit in this car full of sensors, and all these sensors are looking around the car to see the car in front of you. Are you still in the middle of the road? And all this information is sent to a data center, somewhere in the cloud, somewhere in the world. And that data center receives from all the other cars also this information. And then on the data center, they start to calculate. Do we need to speed up? Do we need to brake? Do we need to go a little bit left? Do we need to go a little bit right? And then you make the conclusion, the check, and that you send down the information to the car to adjust the car. My question, dare you to sit in a car like that? Do you feel comfortable if you're driving through the city, speeding with this car, knowing that you forgot you have maybe a little bit fight with your neighbor of 12 years old, the guy, and he's very handy with computers. Maybe he could hijack the system and maybe find your car and maybe change the braking or changing the speed if he want to do something with you. So, but technically, if it belongs to me, I will never sit in a car like that. I want to sit in a car where I have the sensors that looks around the car and makes the calculations and see, hey, my neighbor is coming a little bit closer. Okay, I have to speed up. Oh, I see the road goes a little bit more to the left. And then the local inside the car, the control is taken to adjust the car to speed. And then, of course, there can be, for example, still internet connectivity to the car, but the internet connectivity of the car is not control. The internet connectivity in the car is to inform. For example, if there is a queue ahead, or is there some roadblock, or is there some information, maybe weather information because it become wet, rainy, whatever kind of things. And then I can make the decision to change my route. And that is all local. And this feels much more comfortable to sit in the car. Maybe technically it will be even better, because then we can finally get rid of bad drivers, and maybe to good drivers we get equal drivers, put it in this way. So that is definitely for me very clear. I want to sit in the car. And the stupidity is actually that we start to manage our electrical system as the brown car, not as the yellow car. And that is that worries me, because what I say, if we don't have electricity, we also get killed. It is almost the same as a car accident. So if you have 24 hours no electricity, okay, it's doable. But if you get 1 week no electricity and it's freezing minus 20 degrees or minus 10 degrees, okay, boo, then it's a thingy. So that means we get actually more and more exposed when we start to enable these kind of new services, and we call that cybersecurity. So we build a system what we need to protect, like the car. If you want to make in the brown car, if you want to make it safe, and you introduce cybersecurity to do that, you do a lot of management to prevent that somebody could take that car. And by the way, and that is what is for me always scary in the cybersecurity part. It is like a war, you know. If you have better weapons, okay, then the enemy will not come, but the enemy will have better weapons, and you come in a chain of growing up. So that means you are never safe, you are never protected, because you see also with your computers, almost every day updates for security patches. So it is never done in the right way. So, and the point is, when you enter into this electrical network, okay, you can easily create blackouts. You can easily make physical damages. You can blow fuses. You can trip breakers. You can install ransomware. You can so many things. You can take over control. There's so many things that makes it incredibly difficult, and that's why, in our opinion, my personal opinion, as that is driving me in 𝗀𝗀𝗃, because this is what I really want to prevent. So that is driving me to that part. So okay, and it's okay.
Yes.
Next.
So that's I fully agree with what you're saying, Harry. It's it's very interesting, and that's I made a bracket. That's what we within DG4IC we're promoting, that at human being at the end should always keep the control of the data and the systems, except in very specific conditions which impact the global humanity or the global community, and which are written. But here we are not totally in this field. So we can see that the interconnection today of the networks, combined with massive deployment of cloud managed equipment and systems, perfectly address the challenge of network congestion, while bringing flexibility, agility. But it raises at the same time the issue of vulnerability to potential cyber threats. So, Harry, is it possible then to move towards simple and more autonomous solution based on local control, as you mentioned?
Yeah.
Would the use of direct current in this case, relying on DC grids, help to ensure this resilience? And if yes, how and what would be the advantages? So
yes,
we'll be glad to listen to you.
Very happy to answer that one, because this is the beauty, really the beauty of direct current, and particularly the beauty of 𝗀𝗀𝗃, because technically it doesn't matter if it is AC or DC, because it is energy providing, but the properties and the system design of 𝗀𝗀𝗃 is designed to overcome these big threats. So technically, and to give a little bit small background on that one, 𝗀𝗀𝗃 is designed based, and that is just to make a small example, the Dutch water management system, the water protection system. It's a 1,000-year-old system, and it has made the Netherlands dry. And that is where the same rules that apply in that system we put into 𝗀𝗀𝗃. So that is actually very classic traditional way of management, but still in a high technology environment with these very high robust elements. And to explain that a little bit, is that that is one of the advantages of a DC microgrid. And to explain a little bit what you're doing, if you, for example, operate a laptop, a computer, you can see it as a very, very, very small microgrid. Sometimes you connect to the AC system, you charge your battery, and you can randomly unplug your thing, and your application remains running on the battery. The same is with an electrical car. So you can connect, so you actually take energy, but the risk that you can bring down the electrical system inside the car, or you can bring down the electrical system inside your laptop, is not feasible. Now, and DC microgrid, you can see a little bit as the same. Instead of the CPU that is powered from the battery, it's maybe your washing machine is powered from the battery, your electrical car is charged from that battery, or the PV is entering the energy to the battery as an additional source. So you get these kind of things locally managed with local rules, with a local system, and it doesn't matter if it's connected or disconnected from the AC system. So to balance that local system, it's the same as your electrical car. It's your local sensors, your local decisions, your local management. Everything is done in your own environment without any dependency on the outside. And then you can see, for example, that you can manage multiple sources. And normally, like in the AC system, to manage multiple sources, if you connect it to a big system, okay, you need to know what we call the state of grid. Is the grid oversupplied? Is the grid undersupplied? What do we, maybe the market is going up, we have to drain the battery, or we have to charge the battery, and that we have to control. In the DC microgrid, it's a very simple way. You just look, you put two fingers in the socket, you measure the voltage, and the voltage tells you everything. So if the voltage is high, okay, that means there's too much supply. So the washing machine could say, okay, let's speed up, let's do this program because it's happy hour, we can do that. If the fridge says, okay, I'm -10, I can go to -20, hey, happy hour, let's take it. Let's take that energy to consume. And if the fridge is -10 and the voltage is low because the sun is not shining, maybe the battery start to drain, okay, then the fridge can say, hey guys, I'm still a -10. I have an issue when I come below -5. Okay, let's wait to draw energy. So you get this automatically controlled by the devices, not with a manager, but by the device itself. That means everybody's playing the role in the system to balance. So we don't need an IT layer to manage the sources and the loads to cooperate to find the balance in the system. The same as the traditional AC system in the past, what was centralized generation with local consumption using the frequency balancing act. And now in the DC microgrid, use the voltage in that way. So we go back to a very classic, robust, simple structure to manage without the interference of all these kind of things.
So you mean it's a self-controlled and self-balancing system without outside connection?
Yes, with outside connection and with outside vulnerabilities like digital control. There is no decision, there is no other decision equipment in the system that could want to control something. Every device is autonomously playing a role in the system. And of course, people say, yeah, but you have communication. Of course you have communication. You need to have communication to be informed. Like in the car example, you want to know if there is a queue, if there is a roadblock ahead, or the weather is changing, you can make actions on that one. So still, you can inform equipment, and the equipment makes the decision based on the information to change its role. So that means there is full data connectivity in the system, but it is information providing and is not control decisions. And this is you can do on the level in current OS. And that is one of the reasons why we incredibly reduce our risk for cyber. because there is no control. Nobody can take over. Nobody can turn off equipment. Nobody can speed up equipment from the outside. It's just a decision on the equipment itself. And then there is
sorry, because I see the question, and it's independent of the AC grid, or it
yes,
can be
fully independent on AC grid. And the interesting part of this, and there it comes really back to the beauty, because the almost most beautiful device on this planet today is what we call the interlink converter. This is really the game changer. The interlink converter is a device that is in between two systems. And there again, what I explained, when you make a system, you should be independent of other systems. So if the DC installation itself is a system on its own, like the digitalization is a system on its own, and the AC system is a system on its own. But you need to have an interface to be friendly to the AC system and very friendly to the DC system. And there you can, with the interlink converter, you can play a role. And this interlink converter can be incredibly helpful for the AC system in a very friendly, positive way. And the interlink converter can be incredibly friendly to the DC system. That's why it is the most beautiful equipment on this planet, because it is your friend that makes the handshake between the two systems. And to answer the question a little bit, what happens if the frequency change, for example, if there is too much supply or there's a risk for blackout? Of course, the DC microgrid, the DC system, can support the AC system to provide maybe inertia, artificial inertia through the interlink converter, just looking to the frequency. So you make the reaction from the interlink converter very analog. And the interesting part of it is that the interlink converter, to explain a little bit, is that normally when you have in AC all your converters to the AC system, then you need to manage all these converters to provide that role. And you connect a huge capacity of converters to the AC system. And this creating these congestion issues. An interlink converter will be a much smaller device connecting to the AC system. So the interlink converter will remain within its capacity. So it cannot hurt the system if it cannot oversupply the system. This is one of the rules we have on the interlink converter. So that means you build actually the AC system back to a classic structure from the past 130 years. And the interlink converter can play autonomous based on the frequency, maybe to provide some reactive power if the voltage is too high. Maybe if you see unbalancing in the phases, maybe it can provide balancing functions, maybe can play a role to power quality, but it can do that autonomically. And of course, if you say if you have information from the market, for example, the market provide, like the weather report, provide the market prices. Okay, the interlink converter could make the decision, hey, the user is not at home, my battery is full, the price is good. Okay, let's transfer some energy through the public system, but there is no command who's doing this. It is just a decision that is done in the interlink converter, because the interlink sees, hey, it is happy hour, it's high voltage. Okay, let's push it out to the system. Or opposite the way, you see that the frequency is too high, and you see the voltage is running low in the DC system. Okay, let's push up the voltage a little bit. Let's introduce happy hour, because there is oversupply on the market. And this role makes it, that's why we say current race is incredibly cyber secure, because there is no somewhere else on this planet from a data center or something that needs to say to this interlink converter, and now you have to do this, and to the EV charger, and now you have to do that. That is not the case. It is all done by the devices on the system itself.
Okay, thank you. That's clear. So there is a kind of, let's say, a drawbridge between the AC and DC, and this drawbridge you can connect it or not connect it, and and disconnect it, so get cyber-proof. So if I well understood, if there is a shutdown on a AC grid, would it be possible to keep the DC grid continue to operate?
Yes,
as a island mode independently from the main grid?
Yes, fully, because the interlink converter is not needed, because it's just a support on both systems. Sometimes it support does, sometimes does support. So that means you can disconnect it, and that means the DC system is by default islanding, and that makes it so nice. So it is by default. So that's why in the DC microgrid, if the grid fails, you don't have any transaction, not any transfer effects on the DC side. It's complete autonomous in that way. And one thing I want to highlight also, and that is the sovereignty issue, because what I say, it's the most beautiful equipment on this planet. It is also the most trustful device we have in the system. And if things are trustful, you want to make sure that it cannot hurt somebody else. So nobody is sneaking in something, maybe some control with a backdoor to take control. And that's why I think that like the interlink converter should be a very sovereign device that is really trusted by the grid operator, trusted by the citizens, and it is locally manufactured. You can trust that. So you come here in the case like US for US, China for China, Europe for Europe, these kind of things. I don't like that approach so much, but in a way, when it comes to system critical topics, you create your independency here on this device, and this is why it is so important.
And it goes at a much lower level. You can speak about territories or communities or district.
Exactly.
So that's very important. I'm pretty sure if you speak to a mayor in any kind, any cities, they would love it, because this is a way to save their population.
And that's why we have like the discussion about the second grid, because what we do here on the private domain, because that's why you can do also in the public domain. You can make part in the public domain. You can make a structure that is autonomously independent and provide availability just to power communication equipment. For example, like in Spain, is still a good example. Luckily, there were backup capacity on your transmission towers. That means during the blackout, people could be informed. But when the batteries are drained, you cannot inform anymore. And that means you need to have a little bit self-controlled microgrids that remains active to ensure that you can keep the minimal activities in the public space to coordinate the society, to inform the society, to say, guys, there will be fresh water tomorrow arriving by boat, sailing boat in that case maybe, or whatever. it is arriving or something in these kind of things. So you need to make sure that you keep important things going on during serious events. So the reduced the vulnerability, and that's clear. And the point is, can the DC microgrid, that's why it is cybersecurity by design, because it doesn't need anything of these elements. So if you don't need digital control remotely from outside, of course there's a lot of digital inside the product, but that remain a local activity, like in the autonomous car. That means then you are fully resilient, because there is no external control needed. And that is what makes it incredibly good to do. Maybe you can control some behavior, but you can only control behavior within its limits. So you never you can only come maybe in a comfort situation, but never come in an emergency situation by that. And this is what it makes it very, very clear. So this, there's no centralized control app. There is no cloud services. All the controls inside electronics. There's no IT vulnerabilities, like outdating of the software, that you need to update the software because it always to keep up with the last edition. Cloud is an option. You can connect if you want, but you can send information to the cloud for monitoring reasons forever for things, but it's not harmful. And yeah, it's incredibly transparent.
It's very interesting. It's like I know that you've been inspired as expert and founder of DC system and to control. You've been inspired of the Dutch water system, which is also resilient and which follow this principle of subsidiarity, so bottom up and not top down.
Yeah,
so,
that system
that's exactly the same. So I landed with a 𝗃𝗃 you disconnect in case of problems, and I think then you are in the yellow car, but you can be also in the brown car, but you have the right and the possibility to disconnect. So that's safer and has much more resilient. So it's very inspiring. Thank you.
Right.
Maybe we have questions. Raphael, what do you think?
Prashant, let us know because I am on the slide. Do you have questions that we can share? Or if it's
I think we answered a few of them, but
you can start
few questions.
posting your questions.
Can you hear me?
Yes.
Yes, we have few questions. So few questions from Michael.
Yes, hello. Can you hear me?
Yes, you can also ask directly.
Yes, I the first thing I asked was, are you aware of normal accident theory? And I will explain shortly. This is a guy, 𝗪𝗪, came up with this in the 80s. This was a time when we had all kinds of disasters worldwide, for those who are younger. And his conclusion was, if you make something very complex, and you also make it like a house of cards, like that if something goes wrong, it will go wrong, etc., then an accident is a normal outcome.
Yeah.
And when I look at the way we transform our electricity system, in which we choose to use software, clouds, and all kinds of stuff, we are making a very complex system.
Yes.
Yes.
That is also strongly coupled. And so the outcome is pain.
Yeah, I fully agree.
And I'm still very curious about the cause in Spain, because it could be, and we can make a bet on this, that the safety system caused the enormous blackout.
It could be, yes. And but the point is that actually there's many times a day. There's all the time almost a blackout. How to say it?
Yeah, that's what we call a near miss. Yeah. And a near miss is not a success. This is something very important to realize. In a high reliability organization, a near miss is a serious problem. So we should also regard it.
Now that is why it is very clear. That's why that was really one of the major drivers in 𝗀𝗃 to define a structure that can do this with this high simplicity. So our slogan was always, AC is a simple system with simple components, and now we make a complex system with simple components. And in DC, we make a simple system with more complex components. So we bring the smartness inside the components, like the iPhone today in the telecom world. It's a complex device.
Because the power of electronic.
Yeah. It's a very straightforward way, and it makes it, and in my opinion, I don't see any cyber risk, and we demonstrated in many projects without digital layers to manage and to control the installations. And of course there is data connected, but that's for monitoring. It's just the information. It is not harmful. It's not affecting set points. It's not affecting the behavior of the installation itself. And I think this is very key, but because people now don't know the difference if there is communication involved, it means that control or means that monitoring.
Yeah.
and this should be actually cleared out. And today I see with many companies make new business models, like an HVAC manufacturing provide services to control your HVAC. To be on the market, okay, it sees the price going down, you pay a premium per month for this service, and they manage your HVAC in the most cost-optimized way with control from a cloud. And this is the vulnerability, like your car, like if you take a subscription to manage your car to have the lowest cost of charging. It's the same.
And you have a lot of examples like that, yes.
Yeah.
Prashant, maybe you have another question?
Yeah, my second question is this. If we switch to DC, we have a lot of legacy equipment. And the summum of the result of legacy is Japan. Because Japan has areas that are 60 hertz and has areas that are 50 hertz. So why the hell did they do that? This is all coming back in the 19th century when somebody in Tokyo bought a German generator and somebody in Osaka bought an American generator. And this is, nobody wants this by design. So how do you go with legacy?
It's simple, very simple. Because the legacy was working in the past perfectly. So we believe for the next 50 years in a full hybrid system. And that's why DC is helping AC. And the point is, the issue is coming in the system because we add new equipment. So we don't need to deal with legacy. And all the new equipment, EV chargers, solar panels, battery systems, HVACs, are new equipment. And if you concentrate the new equipment to the DC part, then we don't have an issue in our electrical system because the old 𝗪𝗎 radio, your flipper cars, how to say in English, the game machine, these devices work perfectly and they don't disturb the system. So you can still, you keep an AC system, but you build a kind of hybrid solution. You make in a building a small part in that building DC. You make a small part in the public area DC, and that small part makes this transition of the energy transition possible because it removes our headaches and brings the happiness to the DC part and remove the unhappiness, the headaches from the AC part, and that makes the system simple again and independent. So we instead of changing the system by mixing systems, because that is the complexity. And this is why we introduce a new system that is independent of the existing system, and then make two systems side to side and let one system grow by time. And then it's a matter of who's successful, and maybe it remains like that, because the AC system is a super good system, by the way. It's super simple. So we should not say, of course, when you asked me 5 years ago, I was very fanatic. Then I was kill AC, but now today I love AC, but in a way that we support AC because it is a huge asset. You don't change overnight.
Yes. So anyway,
this is exactly what current OS is trying to do, not to have two different systems, not to have a unified global standard.
Yeah, that is very important, because without a standard, I wouldn't give you a chance. That's really necessary. The point is only that if you look at the Netherlands, we already have in the last 10 years, of actually 6 years or so, we installed huge amounts of solar panels, all with converters that are AC. Yeah. And this system already exists. So how do we? It would be nice if everything was hanging on DC, my car, my batteries, etc. But cannot buy it yet, I guess.
No, it will. That will go very, very fast, because then the interlink comes in, because you are stimulated for self-consumption. Otherwise, you lose your business case.
Yeah.
So. And if you go to self-consumption, you start to introduce a battery. You come today to a hybrid converter, and that hybrid converter will expand to that hybrid situation. And that's why Current OS is focusing on the interlink converter to standardize that one, and focusing on the protection schemes. Because if you do everything in one box okay, you are limited in expansion. So it will be in no time it becomes an installation. And that is what we truly see happening. And so for many use cases, like in buildings, the mailbox is incredibly overflowed with requests of people who have capacity issues. And with the DC topic, you can easily fix that and make it happen. So it is, for me, in a transition time, it's just a matter of a few years, and it will be the standard. At the end of the day, we try to push the interlink converter, if you become a prosumer, that it should be done by an interlink converter instead of everything with many AC/DC inverters in parallel to the AC system with all the headaches as power quality. So, of course, and the equipment is not fully on the shelf everywhere on every store, etc. But that's why we have the community. It is, we cannot, to change the world in one day. It takes a couple of days to do that. So
a couple of days, probably something like a little bit longer, I guess.
But anyway. Yeah.
Okay.
Okay,
Some
you
more
also had the
questions?
question about
Thank you.
Thank you.
about AC microgrid with frequency control.
Yeah, that's also another question, of course. If you say DC, why can it not be AC then?
Yeah, of course you can do that in AC. Simply, you can do that fully. But the point is, it becomes huge complex. An AC microgrid, you need to manage the frequency. You need to manage the voltage. You need to manage the reactive power. You need to manage the harmonics. And in DC, you only need to manage the voltage.
So it's much simpler.
It's so much simpler.
Yes.
And probably also cheaper, I guess.
Yes.
And also cheaper. Yes.
Okay, thank you.
And we think, Harry, this challenge after what we said, isn't it the challenge of the next decade?
Yes.
Because we see, I introduce a ramp up of 50%, a growth of 50% of the electricity consumption. So within 10 years. So this is also the challenge of the next decade. So it's a historical meeting for us.
And the point is, even like for example, it could be an incredibly fast game changer is the vehicle to grid, the V2X, because on the DC part it's logic, and on the AC part it's huge complex. So we expect really that the DC socket on the car will be the bidirectional point, and then with the local converter to see how it interoperates with the system on the back. And then it's a matter of time that the onboard charger will disappear and you get. So this is like a transition. Of course, it takes another few days.
It's a key message what you're saying, and we should push it. I know that Germany has made it mandatory that every cars are bidirectional, and but it's not everywhere the same. And even if they are bidirectional, the user should be able to monitor it and not rely on one company for it. So it's a big challenge for the next years. And I think don't you think that we should push this message at the highest level in Europe, and because we should take the right direction, isn't it?
Yes. And the other perfect example, and that is also a big game change, is the USB-C socket. Even on that small level of power, you see the speed of growing that adaptation to come to sockets today. Even in houses, if you design a new house today, you put your sockets, DC sockets, and if you now with new DC socket of 240 watt. How do you make the AC/DC converter in the wall, in the socket? You cannot do, but the DC you can achieve, and this is a huge enabler also. So these are many things in the background. HVAC control to link the HVAC to the battery, to the PV, the EV connecting to the PV. It's all done by the DC link in the end of the day. So the direction, the wind is in our back for DC on this point. the regulation, the decisions on the high level is all the time indicating actually in DC solution without knowing it, without realizing it.
Thank you.
With that, I will come to the last question. Is it just the famous DC link that we have in instance in ships? I think this question was related to interlink converter.
Now, the DC link is that is why the whole system itself is linked to the DC link, and the DC link is the one who manages. And in 𝗀𝗃𝗃, we wire out the DC link, so it is not the DC link inside one small compartment. We distribute it, and we distribute it because the DC link is also known as incredibly dangerous. And in 𝗀𝗃𝗃, we wire out the DC link in a safe way. That is one of the key elements to make it technically feasible. Because DC was known as dangerous current, but that is a different topic. And the 𝗀𝗃𝗃, it's not dangerous current. It's really direct current again, as it should be.
Good, great. I think that's all we have in the chat. Anyone else have any question? You can open your mic and ask directly if you wish.
No, or we can announce the next steps. So, well, basically, if you're interested in knowing more, you have our contact details here. Contact us in our email box or on our LinkedIn. We can explain you what current OS is doing and how we are changing things, how you can get involved. You don't need to be a partner to know about us. I mean, we can also come to your community, building, office to explain what current OS is and see how you can get involved without necessarily becoming partners of the definition of the DC standard. What else I want to say? Next webinar will be on June 25, and it's going to be centered on the North American implementation of direct current. So for those of you who are from North America today, stay tuned. June 25, we will give you the time soon. It will be late Europe time and midday for the US, early day for the West Coast. And that's it. Thank you for joining today. Thank you for your attention. I will share the recording very soon. And let's stay connected on LinkedIn or by email.
Thank you.
Thank you, everyone.
Harry, Emmanuel, and Raphael, and
Bye.
thank you, everyone,
Bye-bye.
for joining.
Thank you.
Bye.
Bye-bye.